problem involving the pH of a weak base in water. So we've been asked to calculate the pH of a solution of 0.5 molar ammonia. Remember, ammonia is something that we've used in lab a number of times. It's basically the active ingredients in Windex. It's one of those things that you should never mix with Clorox because of a redox reaction that we're not really interested in today. But anyway, so we've been given a hint that ammonia behaves as a base in water. So as always, we're going to try to write a Rice table. Reaction, initial, change, equilibrium. And so to write our reaction, we're going to start with the ammonia. And it's going to react with water. And we're told that it's going to behave as a base. Now remember, Bronsted-Lowry bases accept hydrogen ions from water, whereas the water will behave as an acid and donate a hydrogen ion. So we're going to transfer a hydrogen ion from water, the acid, to the NH3, the base. When NH3 accepts NH+, it's going to become NH4+. Don't forget the change in charge. And for the water, that's going to leave behind OH-. Again, don't forget the charge on that one. All right. So now we have our reaction. So we know that initially the ammonia has a concentration of 0.50 molar. We don't have to worry about the water because water is a liquid. Liquids and solids don't change their concentration during the course of an equilibrium reaction because their concentration is just due to their density. We're going to put a little squiggle here to remind ourselves of that, that we don't have to worry about it. There's no ammonium or hydroxide initially present in the beaker, so we're just going to put zeros under those. All right, so this reaction has to go forward to create something here. It can't go backward because these are 0. So we know that this is going to be minus x. These will be plus x, plus x. Remember, the change row is governed by the coefficients of the reaction equation. Because these are 1 to 1 to 1, our change is also 1 to 1 to 1. So now the ammonia at equilibrium is just the initial plus the change. Initial plus change gives x over here. Initial plus change here just gives x. All right. One thing we have not been given here is the Kb value, so we have to go look that one up. It turns out that the Kb of ammonia is 1.8 times 10 to the minus 5. Now we're going to write our Kb expression. So the Kb expression will be products over reactants. Again, we don't have to include the water. It has a functional concentration of 1 here. Now, let's back up one moment. How did we know this was a Kb? Remember that B stands for base. We're going to use Kb anytime we have hydroxide as one of the products. All right? So anytime you see hydroxide, you know that it's going to be a Kb. We were also warned in the problem that ammonia behaves as a base. So we knew that this was Kb. All right? And to go look up the Kb value for ammonia. Anytime you're not given these values, you can always just go look them up either in a textbook or the easiest way is to just search for them on the internet. All right, so now we're going to plug in, remember our equilibrium row gets plugged into our equilibrium expression. All right, so we're going to have x times x, that's the ammonia, that's the hydroxide, over the ammonium, excuse me, that's ammonium, that's ammonia. After many years of doing this, you'd think I'd get those straight at some point. And that's all going to be equal to our Kb value, which is the 1.8 times 10 to the minus 5. Now, this x is going to be small because we have such a small Kb value. Anytime, remember, we can make a small x approximation anytime this is below about 10 to the minus 3, 10 to the minus 4. So this is a pretty small number. We expect a very small dissociation. So subtracting from 0.5 is not going to matter. So we're going to neglect that guy. And now we're going to simplify. All right. So we're going to have x squared over 0.50 is going to be equal to 1.8 times 10 to the minus 5. Okay. So now moving this over here, we're going to have x squared equals 0.50 times 1.8 times 10 to the minus 5. And I just, you can think of this as cross multiplication, or if you like, we just multiplied both sides by 0.50, either one. So now we're going to take the square root of that and plug that all into our handy calculator. So you could have multiplied these first and then square rooted it. I'm doing what for me is the lazy way of doing it and just plugging it all in all at once. Make sure you have parentheses around both of them though if you do it this way, so that the calculator knows to take the square root of those things after they're multiplied. All right, and that gives us an x value of 0.030. Now, the problem asked us originally to calculate the pH. The x value here is our hydroxide concentration at equilibrium. So we're going to have to do either change this to hydrogen ion, then pH, or we can do POH to pH. I'm going to do what I think is the easier one and do the POH. So the POH is the negative log of the hydroxide ion concentration, which is this value here. So I'm going to do negative log of my hydroxide concentration, and that gives me a POH of 2.5. We were not given a temperature here, so we're going to assume this is taking place at 25 Celsius, which is what we always assume when we're not given a temperature. So that means that the POH plus the pH is equal to 14. And so the pH is just going to be 14 minus the 2.5. Oops. I could have done that in my head. So pH here is going to be 11.5. All right. So when you're encountering these problems, the first thing to do is to write a rice table. After that, write your KB expression, plug your values from the rice table into the KB expression, do all the math, double check what you've been asked to do. Don't just say, oh, I got X, I'm done. Find the POH, convert that to pH.